Today we have Saeed Sharifi-Malvajerdi. Saeed is RAP here in his third year and works on, I guess I would say, societal concerns in machine learning, issues like fairness and strategic behavior and machine unlearning and privacy and connections among several of these things together. And today we'll be talking about fairness in information design and strategic classification.
Thank you.
All right, go for it.
Hi, everyone. I'm going to be talking about fairness and information design and strategic classification. This is going to be based on two joint works with my collaborators, Lee Goldman, Emily Diana, Evan Stangl, Oliver Keelian, and Jules. And I'm going to start with a brief introduction to strategic classification. So imagine that you're in an algorithmic decision-making framework where there is a learner that is using a classifier to make decisions for individuals. And we might call these individuals agents as well, interchangeably. In certain domains, such as loan applications or hiring, individuals have some knowledge of the deployed classifier of the learner. And in these applications, they do benefit from positive classification. So what happens is that given their knowledge, individuals strategize at a cost to look more qualified than they actually are. For example, in loan applications, people know that a higher credit score is better for them and improves their chances of getting a loan. The person might open new credit card accounts in a short period of time to lower their credit utilization and artificially increase their credit score. Obviously, this is just a hacky way of looking more qualified. Like, this is not going to improve a person's financial capabilities. Or in hiring, a candidate can memorize answers to common interview questions. And again, this is just a hacky way to game the system. It's not going to improve the candidate. And the goal of the learner in such settings is to design a classifier that is accurate in its classifications in the presence of such strategic manipulations by the agents. All right, let's formalize this. We have agents in the population that are represented to us by a pair of X and Y. X is the feature vector, and Y is the binary label, whether someone is qualified or not. And there exists a function F that maps feature vectors to labels. This is the ground truth function. We have a distribution D over the space of agents, and there is a function C that captures the cost of manipulation for the agents. So the cost of strategic manipulation from point X in the domain to point Z in the domain is going to be given by C of X and C, which is a non-negative real value number. And one important assumption here is that manipulation doesn't change one's label. If someone is unqualified, no matter where they go or how they manipulate, they're still going to be unqualified. And we'll take calgraphic H to represent the hypothesis class used by the learner. So the learner is going to pick a hypothesis from this class to use for classification. All right, so given this model, now the strategic game between the learner and the agents is going to proceed as follows. This is basically a stack over game, if you're familiar with that. So the learner goes first, and knowing the cost function C, as well as the ground truth function F and the data distribution D, or instead of F and D, or the labeled sample from the distribution, releases a classifier from its hypothesis class. And then every agent in the population best responds to this release classifier by manipulating to a point that maximizes their utility. And what is the utility function of the agents? It's basically the difference of their classification outcome and their cost of manipulation. So every agent X is going to find a Z that maximizes H of C. This is their classification outcome minus C of X. This is their cost of manipulation. And the goal of the learner in such setting is to release a classifier that maximizes its strategic accuracy. And what is the strategic accuracy of the classifier H? It's basically the probability that H agrees with F, the ground truth function, after the agents manipulate. That's why H takes as input the best response of the agents. All right, so this is the game and this is the objective for the learner. And now I want to show you a simple example to show that it is possible to optimize this objective for the learner. So suppose that you're in the d-dimensional Euclidean space and the ground truth function is given by a linear threshold. So everyone above this linear threshold is a positive and everyone below is negative. And the cost of manipulation is basically the L2 norm difference for the agents. So if we use F for classification, ignoring the strategic inputs of the agents, what happens is that the negatives that are within distance 1 of this threshold do have incentive to manipulate to the positive region and get classified as positive. So we're going to make error on those people, the negatives that are within distance 1 of the threshold F. But if we shift F by 1 towards the positive region, and let's call it H, and if we use H for classification instead of F, what happens is that now the negatives do not have any incentive to manipulate because their distance to the positive region is going to be more than 1. They're not going to receive any positive utility by doing that manipulation. And all the positives that are now between F and H in that strip, because their distance is less than 1, they do manipulate to the positive region of H. And all the positives that lie above H are going to remain there. They're already classified as positive. They just sit there. So if we use H for classification, everyone is classified perfectly, and we achieve perfect strategic accuracy.
I'm making the poor people work hard. You're charging them.
Exactly. This is the way to make
Even though they're qualified, you're making them work.
Yeah. Exactly. This is how we make like linear classifiers robust.
All of our faculty applicants have to write their statement of purpose.
All right, with that discussion on strategic classification in mind, let's move on to the second part of the talk, which is fairness and strategic classification. And I want to start with a brief overview of related works in this domain. Overall, this area is underexplored. So there is this work by Mealy et al. From 2019, where they introduced the social burden of the classifier, which is basically the expected cost that the qualified agents have to pay in order to receive positive classification, which is something that you just mentioned. This is called the social burden of the classifier. And what they show in their paper is that, a quick summary of the result is that accuracy maximizing classifiers can cause disparate social burden across population groups. And this is undesirable in terms of fairness. And there's this other work by Lily Hu and others, again from 2019, where they consider strategic setting with 2 groups, one advantage, one disadvantage, such that the disadvantaged group's cost is always higher than the advantage group's cost. And again, they show that adopting accuracy maximizing classifiers can cause unfairness. In particular, they show that by doing so, these accuracy maximizing classifiers can mistakenly accept unqualified agents from the advantage group and reject qualified agents from the disadvantage group. And again, this is not good. At a high level, these works generally consider accuracy as the primary objective of the learner, and they study the social effects of adopting accuracy maximizing classifiers in strategic settings. And this is exactly the point of departure of our work from these works. So we consider enforcing fairness as constraints in addition to maximizing the accuracy of the learner. Right, now let's look at the extra modeling ingredients that we need. So now in this first strategic classification framework, agents are represented to us by a tuple. X and Y are the same as before, feature vector, binary label, and now G is the group membership, where everyone in the population can be a member of one of like capital G groups. There's a distribution D over space of agents. And we take D sub G to be the group conditional data distribution. So basically D sub G is the distribution of X and Y pairs when we focus only on the group G. And now we have group-specific cost functions. So for an agent X that belongs to group G, the cost of manipulation from point X to point Z in the domain is given by C sub G of X and Z. And this is a non-negative real valued number. And one important assumption here is that agents cannot change their group membership. The only features that they can manipulate is they're captured in their X vector.
Question. Is the group membership visible to the classifier?
Yes.
It knows the group.
You can think of demographic groups, for example. That is your group T. And again, we assume that manipulation doesn't change one's label. Take H to be the hypothesis class, as before. And the agent's utility function is going to be similar as well. So for an agent X, member of group G, the utility from manipulating from X to Z when facing classifier H is going to be the final classification outcome minus the cost of manipulation. And agents best respond when they're faced with a classifier and they want to maximize the utility function. This is their manipulated point, ER of X and G to H. And we have the error rates of a classifier H. The overall error rate of a classifier H is simply the probability that H, when evaluated on the manipulated data points of an agent, is not equal to Y when we sample a data point from the underlying distribution. And we have the group error rates, which is essentially the same probability, but now we take this probability with respect to the group conditional data distribution D sub G. And in this work, we consider the minimax notion of fairness, where we say that a classifier H satisfies gamma minimax fairness if it minimizes the maximum group error rate up to an additive factor of gamma. So we say H satisfies gamma minimax fairness if the maximum of L sub G of H is less than or equal to the minimum of such maximums plus some additive threshold of gamma. All right, with this model, now the fairness of our strategic game between the learner and agents is going to be as follows. The learner knowing the cost functions C sub G for all groups and having access to a labeled sample S, which is drawn from the distribution P, releases a classifier. And then every agent in the population best responds by manipulating to a point that maximizes their utility, same as before. And we consider two objectives for the learner in this work. The first one is simply finding a gamma minimax for a classifier. But ultimately, among all gamma minimax for classifiers, you want to be able to find one that minimizes the overall error rates. And this is given by the second objective. Is everything clear so far?
So can H look at G or not? It's like, are you allowed to, for each group, just use a different classifier and then just optimize separately for different groups, or you're not allowed to do that?
We're not allowed to do that. Yeah, the classifier.
That's what I was asking.
I guess what I meant before was that the training data set does have group membership.
But the classifier doesn't.
The classifier doesn't see G. Yeah, sorry for the confusion.
I guess if you could use G, then this would be much easier. You would just separately do the best you can in each group. But here, you're going to have to trade off.
Exactly. Yeah. You could just train a classifier for each group. Right now, I want to show you a quick summary of our results that we have. And before we get to the results, I have one bit of notation or definition here. We say that the cost function C is separable if we can write C of X and Z as the difference of two functions, some function of z minus some function of x. It doesn't matter what these functions are. And we take the max just to make sure that this remains a non-negative number. So it's a cost function is separable if you can separate the effect of z and x in the function. And this was introduced by the work of Hart et al. In 2016, which is one of the early works in strategic classification, and they showed that this is basically a necessary condition to get efficient algorithms in strategic classification.
So just to check, Euclidean distance is not separable.
No. All right, so the first set of results that we have operate under this separability assumption. We show that when the cost functions of the groups are separable, there is an efficient algorithm that finds an approximately optimal classifier when the number of groups is small. And this is because the running time of the algorithm is going to depend exponentially on the number of groups. And more importantly, this algorithm remains efficient both statistically and computationally, even when the hypothesis class of the learner is the set of all classifiers. And this is because essentially when you assume separability, your problem becomes one-dimensional. Like in the case of one group, or in the case of our model, when we have G groups, it becomes G-dimensional. So you can just take H to be the set of all classifiers. So the separability really helps here to get efficient algorithms. And then we consider costs that are not necessarily separable. Because of the work of Hart et al., we know that separability is essential or necessary to get efficient algorithms. So we cannot hope to get efficient algorithms in this setting.
So, sorry, I mean, separability, generally you should only need separability on average under the distribution, right? Or do you, it's sufficient that if for a typical pair of points, because you're measuring error on average, for a typical pair of points in any group, the cost is approximately separable, right? So
That's interesting.
Is that true?
No, I meant let's see that.
It seems right.
I mean, yeah, like sort of.
Yeah, it needs some work. Yeah, like you can make the assumption that like the cost is going to be approximately separable, but
Yeah, I was trying to say, like, when you say Hart et al. Show that it's necessary,
it has to be exactly separable.
But it could be exactly separable under the distribution over to the distribution.
Sorry.
It could be exactly at approximately separable,
Yeah.
right, depending on the distribution.
I guess the sense in which it's necessary, I mean, it's sort of, some classes, like say linear separators, would be totally fine for Euclidean balls. You just find, just like you did, find a classifier, shift it, right? So it's the sense in which it's necessary is kind of if you want to have something, I guess, that works for arbitrary.
Yeah.
So basically converts everything to a height, right? Every point has a height and it's free to move down and cost to move up. And so the only classifiers you're allowed is saying anything here or above is positive, anything below here this height is negative, and that's the only kind of classifier.
Exactly. Yeah, the only classifiers that are relevant here when you use separability is just threshold functions on like these P functions. Yeah. So yeah, in the case of general costs, we cannot hope to get efficient algorithms because we do know that we need separability even without groups and without fairness constraints. But what we can ask for is efficient reductions from fair learning to standard learning without any fairness constraints in the strategic setting. So we basically want to ask for oracle efficiency. And what is oracle efficiency? We want that given an oracle that solves learning problems absent any fairness constraints, we ask whether the fair learning objectives of the learner can be solved using this oracle by calling it only polynomial many times. So this is our problem here. And in doing so, we consider learning randomized classifiers, which are basically distributions over the hypothesis class. And we require transparency. And what do I mean by transparency? We want the random classifier of the learner be drawn from its distribution before any interaction between the learner and the agents occur. So the learner first draws a random classifier from its distribution that it learned, and then shows that classifier to the agents, and the agents best respond to that classifier. So this is what I mean by transparency. The randomness is realized before any interaction occurs, and this is important in getting complex optimization problems, and it helps us develop algorithms. So with this model, we eventually show that there exists Oracle-efficient learning algorithms for the learner when the hypothesis class H has finite strategic VC dimension. And think of strategic VC dimension as a natural extension of regular VC dimension, which was first introduced by the work of Saeed et al. In 2021. So as long as we have finite complexity in the model class, we can have Oracle-efficient algorithms when costs are not necessarily zero. All right, now I want to tell you briefly about the high-level description of the algorithm that we have for general cost functions. So we want to solve this problem. We want to minimize over all the distributions in our domain the maximum group error rate, where now the error rate is computed is basically the expected error rate with respect to the distribution of the learner. So what we do is that we view this min-max problem as a two-player zero-sum game. One player has strategies over the distributions, and the other player has strategies over the groups. And then we use the no-regret dynamics to find an approximate equilibrium of this game. And what is no-regret dynamics? It was first introduced in the work of Fund and Shapir in 1996. They show that in two-player zero-sum games under some additional constraints, if you simulate an iterative game in which one player best responds and the other player uses a no-regret learning algorithm to update the strategies, then eventually, if you take the empirical average of the players' strategies, that pair of empirical averages is going to form an approximate equilibrium for you.
Is this basically multiplicative weight update, or it's?
You can use the multiplicative weight update as the no-regret. Yeah. So we can use the no-regret dynamics here, and what we need to show after is that we need to show that the approximate equilibrium guarantees that are given to us by the no-regret dynamics can be converted back to the optimality guarantees of the original optimization problem. So we essentially start with an optimization problem, a min-max problem. We take it to game theory space. We frame it. We view it as a two-player zero-sum game. You find equilibrium, and then we convert our guarantees back in the form of optimality guarantees of the optimization problem. So finally, we conclude that the output of this no-regret dynamic space framework serves as an approximately optimal solution to the original optimization problem. Now I want to show you the pseudocode of this no-regret dynamic-based algorithm. So this algorithm takes as input the data set, the group cost functions, and the desired gamma parameter, which is the threshold that we can tolerate for unfairness. It starts with setting the number of iterations of this iterative game and the learning rate of the no-regret learning algorithm. It's not important what these numbers are. It makes some initialization, and then it starts this iterative game. In each round, the primal player, which we call the learner, update its strategies by best responding. And in doing so, it uses a learning oracle, which I call this WERM. It's basically the best response of the learner can be written as a weighted empirical risk minimization problem. So this is what the primal player does. And then after the dual player, the second player, updates its weights over the groups. by using the exponential weights update. This is an order. And this goes on for T rounds, and eventually we output the time average play of the players. So the way that you should think of this algorithm is as follows. Like in each round, the learner learns the classifier. And then the dual player looks at the loss for each group and then adjusts the weights of these groups based on how much loss they suffer. Like if a group has high loss, it's going to receive a high weight in the next round. So the dual player basically corrects for fairness here. And then this goes on for T rounds, and then we take the time average. And we have the theoretical guarantee of this algorithm. It's very similar to standard agnostic packed learning guarantees. I don't want to get into the details of this. Like this theorem tells us that as long as a hypothesis class has finite strategic BC dimension with high probability over the draws of the data set, this algorithm outputs a gamma minimax for a model as long as the sample complexity bound is satisfied. And this tells us that we want the smallest group size to be at least in the order of the BC dimension divided by gamma squared, ignoring all the log factors. All right, so we have the algorithm, the theoretical guarantees. Now I want to talk about some experiments that we did with this algorithm. And it is important to run experiments with this algorithm because one important assumption that this algorithm has is that there is a perfect learning oracle that we can use to update the learner's strategy every round. And in practice, we never have a perfect learning oracle. What we have is heuristics. So we worked with linear threshold classifiers. And for the oracle, we took the paired regression classifier heuristic that has been used previously in many works. This is one sample. And this has been used previously in non-strategic settings, but we need to modify it to account for strategic manipulation of the agents. And the modification that we have on this heuristic, and I don't want to get into the details of this heuristic, is think of an algorithm that outputs a linear classifier. It's not important how it finds that linear classifier. And the modification that we have on this heuristic is that similar to the example that we saw earlier in this talk, we need to make it robust to strategic inputs. So we let this heuristic take as input a shift parameter rho. It finds the linear classifier, and then eventually it shifts this linear classifier by rho towards the positive region to make it robust to strategic inputs. And we take the cost function of the agents here to be the L2 norm difference divided by tau g, and think of tau g as the manipulation budget that the individuals in group G have. So a higher tau g means that cost of manipulation for agents in group G is going to be smaller, which means that their manipulation budget is higher. Similarly, if the group's tau g is small, it means that their manipulation budget is smaller. And what we do is that we compare our method for finding a FIR classifier with two baselines that we design. The first one, which I call non-strategic learner, basically ignores the strategic inputs of the agents and just performs learning without considering the strategic inputs. And the second one, which I call naive strategic learner, this is going to be similar to the first baseline, but it accounts for strategic manipulation of the agents in a post-processing step. So this baseline is going to find a linear classifier, and at the end, it's going to shift this linear classifier, make it robust to strategic inputs. Right, so the way that this baseline deals with strategic inputs is a simple post-processing step, whereas our algorithm takes care of strategic inputs while it learns the model. And we have a variety of results on different data sets and different settings. here I just want to show you one sample plot that we have in our paper. So this is on the hard data set. And on the x-axis, we have the manipulation budget for the agents. Y-axis shows the maximum group error rate of the models. And what each of these four plots show is like the F that you see under each subplot shows how we distribute manipulation budget across the two groups that we have in the population. So when F is 1 and 1, it means that both groups have the same manipulation budget. Or when F is 1 and half, it means that the first group's manipulation budget is double the second group's manipulation budget. And in these plots, the green curve corresponds to our algorithm, the orange one corresponds to naive strategic baseline, and the blue one corresponds to non-strategic baseline. And we show that in almost all cases, at least in this data set, our algorithm outperforms the other two baselines because it achieves a lower maximum group error rate across a variety of manipulation budgets.
The one in the upper right, it's behind the legend, is it that the naive one is actually doing worse than the non-strategic? When the manipulation budget is sufficiently high?
So
Does it
here,
pass?
it doesn't pass it.
It doesn't.
It doesn't pass it.
It shouldn't.
The natural ordering is green, orange, and blue. And I think this is, except for the first one, when we have similar manipulation budget for both groups, they do satisfy this order. All right, this is all I wanted to tell you about this part of the talk, which was on fairness in strategic classification. The last part I want to focus on the paper, which is on the topic of information design in strategic classification. And I want to start with noting that one common assumption that exists in strategic classification is that agents fully know the deployed classifier of the learner. And this is obviously an unrealistic assumption because, for example, in known applications, people know that the higher credit score is going to benefit them, but they don't know the exact relationship between credit score and their odds of getting a loan. They don't know the exact parameters of the models. And because of this, we introduce a new model for strategic classification in which agents have a distributional prior I over the hypothesis class H. And this distribution captures their belief about the deployed classifier. So for every classifier H prime in the domain, I of H prime is going to be the probability that the learner is going to deploy H prime from the agent's perspective. This is what the agents think. And I want to emphasize here that the learner in this model that I'm going to introduce shortly is committed to use a fixed classifier, which we use little h to denote this classifier. And pi only captures the agent's belief about this classifier. And the only minimal assumption that we make here is that the support of the prior must contain this deployed classifier H. That's the only assumption that we require in this model. All right, now, given that agents only have partial knowledge about the deployed model, we equip the learner with the ability to release partial information about its deployed classifier H. And the goal here is that using partial information release, maybe the learner can influence or reshape the belief of the agents about its deployed classifier, hopefully to gain it in its accuracy. But the natural question is, how do we model partial information? And we use subsets of the hypothesis class to model partial information in this setting. So when the learner releases a subset H, it means to the agents that the deployed classifier is going to belong to the subset. So this is how the learner interacts with the agents. And this is going to give us a nice spectrum for how much information we want to release. On one end, if H is the entire hypothesis class, this is going to correspond to no information release. And on the other end, if H only contains the diploid classifier H, this is going to correspond to full information release, which is the standard setting of strategic classification. And this is a very general model of information release. For example, like any common way of information release about a classifier that you can think of, releasing relevant features of the classifier or releasing top K features, which are features with the highest weights. These all can be captured using subsets of the hypothesis class. And when it comes to information release, the only restriction that we have is that we ask for truthful information release, which means that the subset H must contain the diploid classifier little h. So we don't want the learner to lie to the agents. This is the only restriction that we have here. And what happens after H is released? The agents first update their prior belief pi by projecting this distribution onto the subset H. And we use pi sub H to denote this posterior belief of the agents. So for every H prime in the domain, the probability weight under pi sub H of H prime is going to be pi of H prime, this is the prior weight, divided by the total weight of the subset H. If H prime belongs to the subset, and if not, this is going to be 0. So this is basically a simple projection onto the subset. And then the agents are going to best respond by manipulating to a point that maximizes their utility. And what is their utility in this setting? Their utility is the probability of receiving positive classification outcome minus their cost of manipulation. So the utility from manipulating from X to Z when faced with subset H is going to be the probability that H prime of C is 1 when H prime is sampled according to this posterior distribution minus the cost of manipulation. And now we have the strategic game between the learner and the agents in this model with partial knowledge of the agents and partial information release of the learner. The learner goes first, and knowing f, d, cost function c, and the prior phi, it releases a subset of the hypothesis such that the diploid classifier little h belongs to this subset. This is the constraints of truthfulness. And then every agent is going to best respond by finding a point that maximizes their utility. And similar to what we saw before, the goal of the learner here is to release a subset of the classifiers that contains the diploid classifier such that the subset maximizes its strategic accuracy. And strategic accuracy, same as before, is the probability that little h, the diploid classifier, agrees with f after the agents commit to their manipulation. So we have this new model of strategic classification that considers partial information release. And the first question that you should ask is this ever useful? Can the learner gain accuracy by releasing partial information instead of full information release of the standard strategic classification? And we use several examples in the paper to show that the answer to this question is yes, we do gain in accuracy. And this is one such example. So suppose that the space of agents is the interval from 0 to 2. And the data distribution is simply a uniform distribution over this interval. And let's take the threshold function of 1.9 to be the ground truth function. Anyone above 1.9 is going to be a positive, anyone below is going to be a negative. Take H to be all the threshold functions in this domain. And one natural cost function that we can consider here is this cost function. The cost of manipulating from x to z is going to be z minus x if z is greater than x, because higher values are desired here, because they only get you closer to the positive region. And if z is smaller than x, this is going to be 0. Like moving backwards in this domain is going to be for free. And it is easy to show that under the full information release model, which is a standard setting of strategic classification, the optimal accuracy is going to be achieved by h sub 2, which is the threshold function on 2, and its corresponding strategic accuracy is going to be 0.55. And this is because when you use a threshold function on 2 for classification, all the negatives that lie between 1 to 1.9, because their distance to 2 is less than 1, they have incentive to manipulate and get classified as positive. So that region is going to be your error region of the classifier, and probability weight of this region is 0.45, and the accuracy is going to be 0.55. Right, now let's see what happens if the agents have some prior instead of knowing exactly what the classifier is. So suppose that the agents think that with probability 0.9, the deployed classifier is going to be a threshold function of 1.8, and with probability 0.1 is going to be a threshold classifier on 2. This is prior. And now if the subset that the learner releases is the threshold on 1.8 and 2, which is basically the support of the prior, then the posterior distribution of the agents is going to be the same as the prior, because this is essentially the support of the prior. And with simple calculations that I don't want to get into, we can show that once this information is released, given the utility function of the agents, all the negatives are going to remain under 1.9, and all the positives are going to manipulate to 2. And as a consequence, everyone is going to be classified correctly. So the conclusion is that under partial information release of this subset, and when H2 is deployed for classification, the learner achieves perfect strategic accuracy of 1, which is much bigger than the 0.55 of the full information release model. Right, so partial information release can be useful as well. This is the takeaway message from this example. Right, now let's look at the learner's information release problem. This is essentially what the learner wants to solve. The learner is facing a population of agents with prior phi, cost function c, and they want to maximize their strategic accuracy. And the first thing to note here is that including anything outside the prior support in H is not going to influence the agent's best response. Because when a subset H is released, agents are going to project their prior onto the subset. So if you include something which is not in the support of the prior, that's not going to change it. So we can rewrite this optimization problem like this. So we want to find a subset of the support of the prior that maximizes this objectiveness. And obviously, one naive algorithm is to enumerate over all the subsets of the prior support. But this is inefficient, and the question is, can we do better than this? And we show that in certain settings, it is possible to do better than this naive algorithm. And the setting that we consider is basically classification of the agents based on real value test scores. So we consider settings in which there is a function g such that the ground truth f can be written as a threshold on g. So think of g as a test score of the agents. We're going to say one agent is qualified if their test score, which is their g function, is going to be at least some threshold t. And in this model, this setting, higher values of G correspond to higher test scores, therefore they're better for the agents. And because of that, one natural way of modeling the cost of manipulation is as follows. The cost of manipulating from point X to Z is going to be G of Z minus G of X. If G of Z is bigger than G of X, and it's going to be zero otherwise. So getting a higher test score is going to be costly, but getting a lower test score is going to be. And we work with threshold functions on G. This is the hypothesis class. And one thing that I want to note here is that this setting that I described here is very closely related to the notion of separable cost that I introduced earlier, because it essentially enforces the same one-dimensional structure of the setting.
Is it not identical to separable?
It is identical. And here is a summary of the results that we have for this model. First, we have a negative result. We showed that for any prior pi, or a set of threshold classifiers, the learner's information release problem is going to be NP hard, and this comes from a reduction to subset sum problem. So we have bad news here, but we're not going to stop here. If it doesn't work for general priors, we can make assumptions of the prior distribution and hope that it's going to help us to get division properties. So we consider discrete uniform priors. We show that there exists an algorithm that for any n, any uniform prior over a set of n classifiers, and any data distribution, this algorithm returns a subset in time n cubed, such that the subset includes the diploid classifier and that the subset maximizes the accuracy. So we do get efficient algorithm for discrete uniform priors. And then we also show that even when we impose additional structure for the priors, in particular when the prior is uniform over an interval, then we can actually write down the optimal information release in a closed form.
For general priors, is it also hard to kind of approximately solve the learner's problem? Let's say to have epsilon additive accuracy.
So we don't have the result for that, but we suspect that it's going to be hard even for approximation. So far we focused on misclassification rate as the objective of the learner, but there are settings in which the learner's objective is to minimize the false positive or false negative rates. And the question that we ask is that what does optimal information release look like without restricting ourselves to uniform priors? And we do have some results here. We show that for any prior pi, if your objective is to minimize false negative rates, then the false negative rate of the subset, which only contains the diploid classifier, this corresponds to full information release, is smaller than or equal to the false negative rate of any other subset. So this theorem basically tells us that full information release is optimal for false negative rate minimization. And when it comes to false positive rate minimization, we show that for any prior pi, the false positive rate of the entire model class, which corresponds to no information release, is going to be smaller than the false positive rate of full information release. But we don't know what the optimal information release looks like here. All we know is that no information release is preferable over full information release. And we do show, using several examples, that when we want to minimize false positive rate, the optimal information release can be anywhere in this spectrum from full information all the way to information. All right. Now I want to use the rest of my time to talk about a few directions for future work. Like one direction. So as we saw in the first part of the paper, the talk, fairness in a strategic classification considers population groups with differing cost functions. And this differing cost functions is the primary reason for unfairness. But what comes up from the second, or like the information design part of the talk, is that another cause for unfairness could be that population groups have differing beliefs about the classifier, which is captured by this prior distribution. So ultimately, we want to be able to study fairness when we have different groups in the population that have different cost functions and also different prior distribution. And one question that might arise here is that what if one group has the better prior and the better cost function? For example, you have the majority group or the wealthy group, they're better informed about the classifier, and they also suffer less cost for manipulation. And the question is, can we release information in a way that helps the disadvantaged group in such settings? And there is an example here that answers yes to this question. We can hope to actually help the disadvantaged group in such settings where one group has the better prior and the better cost function. So consider two groups, advantage and disadvantage, and three classifiers, H, H1, and H2. And H is the diploid classifier here. So the advantage group is going to think that with probability 2/3, it's going to be H. The learner is going to use H for classification, and 1/3 H1. And similarly for the disadvantage group, we have the prior. And here, when the subset that is released by the learner is H and H1, then we can see that the posterior distributions are going to be as follows. So after the agents project onto this subset, the advantage group's prior is not going to change. It's going to remain the same because the subset is just a prior support, but the disadvantage group is going to exactly know that what classifier is going to be support classification. So by using this form of information release, we basically flipped the quality of the priors for these groups. And we can hope that this can compensate for the lack of resources, which comes from the worse cost function for the disadvantaged group. All right, so this is a motivating example for this studying fairness with differing cost functions and differing prior distribution. And thank you for your attention. And this talk was based on 2 works that you see here if you want to read more.
Questions?
So if I understand correctly, the learner needs to know the prior exactly.
Yeah.
Do you have thoughts on the box? It seems pretty strict. Do you have thoughts on the box assumption?
So we imagine that if you ever want to use this in practice, the learner, for example, hiring a company, can look at historical data of previous hires that they have before, surveys to see what they thought they would face in this hiring process. But we don't have any formal work on this. It's just how we would think that this can be applied in practice. Just look at historical data, run surveys, and see what we get. But yeah, that's a good follow-up question on this as well.
Yeah, also on that second part. So the assumption is that the agents are in some sense myopic in that they see the capital H, they take their prior pi, they restrict it to pi to capital H. Okay, say, okay, pi given that. You could imagine agents that say, you told me this capital H. If little h was over there, you would have told me something different.
Yeah.
And so, like, for example, the fact that you said 1.8 and 2 was really 1.8. You wouldn't have said 1.8. You would have said something else. I wonder if it's like, is it possible to analyze that kind of situation? And
yeah, that's a great point. And yeah, we do assume that the agents are myopic. They just perform a Bayesian update. They don't think why this information is released, but that's a really good, direction for future work as well.
For the first part, is there any connection between accuracy fairness and the social burden fairness you talked about? Like for your algorithm, does it also do better in terms of social burden?
So no, like so when those works, they the way that they look at fairness is based on the cost functions, how much cost an agent suffer in order to receive positive classification. But we look at fairness from the outcomes perspective. We just want to make sure that when we look at the outcomes, no matter how they manipulate or how much cost they, we want to be fair. So it's a different perspective on fairness. They look at from the cost perspective, we look at from the outcomes perspective.
So for the 1.8 and the 2 examples, so over there you showed that like sometimes releasing partial information is better compared to releasing full information to minimize like error rate, right?
Yeah.
Okay. Is there like an example that releasing no information, like is like sometimes that releasing partial information is better than just not releasing any information? Like, do you ever gain by releasing partial information over just not releasing anything?
Yeah, so like in that example that it showed, like when I use the term partial information, that actually is no information because we release the support of the prior.
Right.
But we do have an example in the paper that we showed like the optimal information release is in between. It's neither no information release nor full information release. So it could be anywhere in this spectrum.
We thought about like proximity optimizing. So you said it can be hard to get the. We think about the general case, not the uniform case. It's hard to find the the best partial information. So can you do it for any approximate? In some sense,
Again, like that's a great question and like a great avenue for future research. I haven't done any formal work on it, but I think it would be interesting to see. But like I said, like I feel like when you have general priors, you don't make an assumption on the prior. The problem, I think, or we think, the authors think that it's going to be hard.
All right, thanks.